Yeah, so we're very happy to have Morgan Wheeler, who's going to start us off today by telling us about infinite staircases of symplectic embeddings of ellipsoids into Hirzebruch surfaces. So take it away.
Thank you, Danny. Thank you so much for the opportunity to speak here. So so as you said, I'm going to talk about infinite staircases of symplectic embeddings. And this is all joint with Maria Bertozzi, Tara Holm, Emily Ma, Dusa McDuff, Grace Mokioma, and Anna Rita Pierce. Okay, so recall Gromov non-squeezing. So if we have the standard symplectic form on C2 and two domains in C2, or equivalently R4, we say that one symplectically embeds into the other if there is a smooth embedding which pulls the symplectic form, the standard symplectic form, back to itself. And sort of one constraint that immediately arises is that symplectic embeddings are volume preserving. So if X symplectically embeds into X prime, then the volume of X has to be at most the volume of X prime. And so what Gromov proved is that this isn't the only constraint. So if we have the ball, which is not the ball of radius C, but the ball of where a disk, which is a plane slicing through the ball, has area C, and cylinder, similarly, where the first C factor plane slicing through the cylinder has area big C. If B of little c symplectically embeds into Z of big C, then little c is less than or equal to C. But the point is that there's no obstruction in terms of volume in this case because the cylinder has infinite volume, the ball has finite volume. So you could construct a volume preserving embedding very easily, linearly in fact, but you can't construct a symplectic embedding. So there's something more mysterious happening. So in 2012, McDuff and Schlenk sort of took this to the sort of understood this very well using what's called the Fibonacci stairs. So instead of thinking about the ball, let's think about the ellipsoid, which is pairs Z1, Z2, and C2, where pi Z1 absolute value of Z1 squared divided by A plus pi absolute value of Z2 squared divided by B is less than or equal to 1. And we define the ellipsoid embedding function to be the function that sends numbers A greater than or equal to 1 to this infimum of mu greater than 0, such that the ellipsoid 1A symplectically embeds into the ball of area mu. And we know that from the volume obstruction that, so if you take the inequality ellipsoid, volume of ellipsoid has to be at most the volume of the ball, then you get that C0 of A is greater than or equal to root A. And what McDuff and Schlenk proved is that C0 is piecewise linear or smooth, and it's non-smooth at infinitely many points. And so this is what happens is when A is large, C0 of A is equal to, actually equal to root A. So this means that a subsequence of non-smooth points has to accumulate somewhere. And it accumulates from below at tau to the fourth tau squared, where tau is the golden ratio, 1 plus root 5 over 2. So some pictures. On the left, here is a plot of C0. So you can see that the stairs sort of accumulate from the left. You can only really see a couple of big stairs in this plot, and they accumulate at this point, as you can see at the right, with a coordinate tau to the fourth, which is approximately 6.85 something. And so the orange curves in all of my plots are going to be the volume obstruction. The blue is going to be a plot of the ellipsoid embedding function. And here on the right, the gray is just the parameterized curve, A equals tau to the fourth. So you can actually see where this accumulation point is supposed to be. And you can't see it in the right-hand picture, but there are actually more sort of stair steps after this. There are more non-smooth points to the right of the accumulation point, but they don't have the same structure as the ones to the left. So the steps, a couple of things to notice, the steps ascend from below, and the x coordinates of the outer corners are A coordinates are A equals 2, A equals 5, 13 over 2, 34 over 5, 89 over 13. So these are ratios of odd index Fibonacci numbers. So you can see that the denominator in the nth place is the numerator in the nth minus 2 place. So that will come back later. Okay, so we can generalize this story to toric domains. So a toric domain in C2 is the preimage of a region in the first quadrant under this map. Z1, Z2 goes to pi absolute value of Z1 squared to pi absolute value of Z2 squared. So here are some examples. So A is the image under this map of the ball. B is the image under this map of the ellipsoid 1, 2. C is the image under this map of the polydisk 1, 2, which I haven't defined, but basically you can just think of it as the preimage of a rectangle under this map. And D, well, it doesn't have a great name as a toric domain, so I'm just going to give you the name that it has when you think of this omega as a Delzant polytope instead. So this is the Delzant polytope of CP2 blown up at a point with blow-up weight 1/3. And that might be confusing because these, I mean, especially A and B actually have, well, A especially, has an actual different name as a symplectic toric manifold, a closed manifold, than as a toric domain, right? It's the Delzant polytope of CP2. But for using a result of Cristofaro, Gardner, Holm, Mendini, Pires, in these cases and a few more, if you have an ellipsoid that embeds symplectically into X omega, the toric domain, with a given moment map image, it's equivalent to having a symplectic embedding of the ellipsoid into the symplectic toric manifold. This isn't necessarily true for all symplectic embeddings, but it'll be true for these omegas and for ellipsoid embeddings. So that sort of justifies me confusing notation and sort of calling the picture in D the sort of the toric domain corresponding to CP2 blown up at a point. So we can generalize the ellipsoid embedding function. So if we instead think about the infimum, so it's again a function from values of A greater than 1, greater than or equal to 1, to R. And it's the infimum of values mu, where the ellipsoid 1A symplectically embeds into X scaled by mu. And again, this has to be greater than or equal to a volume constraint, because symplectic embedding means the volume of the ellipsoid is at most the volume of the ball. And if A is large enough, then again, this is not obvious. If A is large enough, then this ellipsoid embedding function actually equals the volume constraint. So if the ellipsoid is skinny enough, it can fully fill X omega, or X. Sorry, I realized there should be X omegas decorating all of these X's. So we say that Cx omega of A has an infinite staircase if it's non-smooth at infinitely many points. So as in the case of the McDuff-Schlenk Fibonacci stairs. So what we know so far, if omega has integer vertices, we know the most. And there's been a lot of work in this area. And in a recent preprint, Cristofaro, Gardner, Holm, Mendini, Pires find 12 omegas where X omega has an infinite staircase. All of these staircases are ascending, like the Fibonacci stairs. And in particular, they found this toric domain corresponding to CP2 blown up at a point with weight 1/3 has an infinite staircase. And they conjecture that there are no others. So what that means is that, it doesn't matter if you scale your omega or your X omega, right? That's just going to change. That's just going to scale the ellipsoid embedding function. It's not going to actually change it or change whether or not it has an infinite staircase. So basically what they're saying is that up to scale, there should be no other integer, no other omega with integer vertices that have infinite staircases. So there's one result about omega with rational edge slopes and irrational vertices. So Usher found infinitely many, in fact, a sort of doubly infinitely indexed sequence of ascending infinite staircases for polydisks P1b, where B is irrational. And this is the case that we're going to be interested in today. So we're going to think about other infinite staircases in other domains with rational edge slopes and irrational vertices. And then when omega has irrational edge slopes, nothing is known right now, as far as I know. Okay, so the first new infinite staircase we've found, if you take this Hirzebruch surface, which is CP2 blown up at a point with weight B, and so it's Delzant polytope is the trapezoid with corner, so it's got a corner at B, 1 minus B, and then the other corners are 0B on the y-axis and 1, 0 on the x-axis. Sorry, 0, 1 minus B on the y-axis and 1, 0 on the x-axis. And we're going to let C sub B denote C sub x sub omega sub B because that's too many subscripts. And here you can see another example of omega sub B. So here we have omega sub B0, where B0 is this B0, approximately 2.7677, etc. And we have found that CB0 has an infinite staircase, and its steps descend to accumulate at this number, which you know will be given meaning later. Okay, so what does this look like? So we have different programs that can plot different things. So that's why the staircase is plotted using several different plots. But the so again, the orange is always the volume constraint, and the CB0 is the maximum of the blue and the little red steps. So you can see that. So for example, up at the top, you can see that the red is like significantly above the blue. So the actual CB0 doesn't include the blue part that's underneath the red part. And so there are lots of steps, and there are steps accumulating to where the green line crosses CB0. And that's that point where the green line crosses CB0, and the volume constraint is the accumulation point of the staircase. And there are infinitely many steps descending to that accumulation point. So a couple of things to notice about the staircase is the steps are descending, and well, so if you've seen other infinite staircases, it doesn't quite look exactly like them because there aren't full fillings in between the stairs. But yeah, so the main thing is that the steps are descending. So we actually have found a lot more infinite staircases, or a lot more things that we are fairly certain are infinite staircases. So remember, this is omega B is the convex hull of these points, and here again is omega B0. And from Christopher Gardner, Holm, Mendini, Paris, we have this quadratic equation, which tells us the x-coordinate of the accumulation point of an infinite staircase. So if I vary B, then I know exactly where its infinite staircase has to appear. And this is proved using these exceptional classes that were introduced by McDuff and Schlenk. But there's also a way to sort of heuristically see this result using the asymptotics of ECH capacities. So, and furthermore, the accumulation point will always be on the volume obstruction. So this equation tells you the x-coordinate of the accumulation point given B, and the fact that the accumulation point is always on the volume obstruction gives you the y-coordinate. So here is the parametrized curve. So we're going to denote the larger, right? So if I go back one slide, the x-coordinate is the larger of the two solutions to this equation. And if I can parameterize that curve. So I'm going to call this x-coordinate AC of B, and I'm going to parameterize the curve AC of B as the x-coordinate, and then the volume constraint, the fact that the accumulation point has to be on the volume constraint as the y-coordinate. And so B is increasing from the black dot towards the red dot and then up towards the right. And it will go off infinitely far because this volume is going to go, the volume of x sub omega sub B goes to 0 as B goes to 1. And the black dot is the accumulation point of the Fibonacci stairs where B is 0. And the red dot is the accumulation point of the B equals 1/3 stairs that Christopher Gardner, Holm, Mendini, and Paris found. And yeah, and another thing to note is that Mathematica decides where it puts its axes. So, right, these axes don't cross at the origin. Okay, so what we expect to be true is that there are 5 infinite sequences of these where C sub B has an infinite staircase, and their accumulation points are plotted here. So there's, again, the black dot that now has a little orange dot in the middle is the Fibonacci stairs. The red dot is the B equals 1/3 stairs. And there is an infinite sequence of orange that sort of decrease to x equals 1/6, or sorry, a 6. There's this cyan or light bright blue sequence that's increasing towards a equals 6. And well, yeah, to accumulate at a equals 6. And then there's a pink sequence and yellow and brown, and they both go off for B values getting higher and higher as high as you want. Or sorry, all 3 of those do. And it's hard to see as B gets large, but for the smaller values of B, you can actually see that the brown accumulation points are, the brown staircases occur for smaller B values than the yellow, than the pink. And then as B gets larger, this window sort of shrinks, and so it's harder to see exactly what's happening. And we think there are many, many sequences of infinite staircases. Okay, so what's happening near B equals 1/5? Our staircase B sub 0 is the leftmost bright blue point. So it's this one just below the red. And one thing to note is that the minimum of the y coordinate of the accumulation point occurs at B equals 1/5. And that's where the accumulation point is at 6. And C 1/5 likely doesn't have an infinite staircase. So here's C 1/5 near the accumulation point. So where the accumulation point would be is at the a equals 6 coordinate, mu equals 2.5. So it would go right through this point where the C 1/5 hits the volume constraint, but it doesn't look like this has an infinite staircase. Okay, so how did we find these? So X omega has what's called ECH capacities, and it's a sequence of symplectic capacities, and the utility is that they obstruct symplectic embeddings. So each of them is a symplectic capacity. So if X omega embeds into X omega prime, then the ECH capacities of X have to be at most those of X omega prime. And if omega is convex, then it turns out that you can completely characterize the ellipsoid embedding function using capacities. So you can compute it as the supremum over K of Ck of the ellipsoid divided by Ck of X omega sub B. And this is helpful because Ck of X omega when is combinatorial. And when omega is simple, such as the trapezoids we're considering, it's even faster to compute it. So this figure illustrates Christopher Gardner's result. So you can see, again, orange is the volume obstruction and blue is C0. C0 it's mostly covered up, but you can see it a little bit at the top. And then the obstructions from the second ECH capacity, the 5th and the 20th are in blue, bright blue, pink, and green. So this is, again, the Fibonacci stairs of McDuff-Schlenk, and you can see that the second ECH capacity is what gives you the first little step. The 5th is what gives you the second. The 20th is what gives you the third. So this is great news, but we still have to take a supremum over an infinite set, so we're never going to be able to get our computer to do all the work for us. So how are we going to do this? Well, we compute for a lot of values of B, 25,000 ECH capacities, and using the Christopher Gardner result, we get this first inequality. C sub B is greater than or equal to this maximum. And then if the maximum is actually strictly greater than the volume obstruction at the accumulation point, then we know that B can't have an infinite staircase. So here's some examples. So again, volume obstruction is orange, C sub B is in blue, green is the parameterized accumulation point curve, and in bright blue is the obstruction from CK. So in figure A, K is 125, and you can see that here CK divided by CK, so C125 divided by C125 is greater than the value of the volume obstruction, so we can't have an accumulation point. And you can see that as you vary B, maybe this capacity that obstructs at the accumulation point varies. But what seems like good news is as we approach this value, so remember B0 is like 2.7677, right? So we're getting sort of closer to that value, and the capacity that's obstructing at the accumulation point is going up. So maybe we have an infinite staircase near these values of B. Okay, so each capacity rules out an infinite staircase for a certain intervals of B. And it's kind of difficult to compute what this interval is for any B, but just from plotting these obstructions, we know that that, for example, the 1/25th, so computationally, we know that the 1/25th capacity rules out all values of B between, for example, 0.277 and 0.32475. These aren't exact, but we know at least for those B, we can't have an infinite staircase. And similarly, we can't have an infinite staircase for B between 0.274398 and 0.27643. So now we've ruled out the B's, we have to look for staircases in what's left. So the trick is, we know that in all known infinite staircases, the x-coordinates of the outer corners of the stairs have periodic continued fractions. So remember, the McDuff-Schlenk Fibonacci stairs have these outer corners given by ratios of Fibonacci numbers. And if you look at the pattern that the continued fractions of these ratios have, they all go 6, some number of 1, 5 repeating, and then either 2 or 1, 4 at the end. And so what we did is we looked within the values of B that were left for sequences A sub k, where A sub k is a periodic continued fraction, and A sub k approached the accumulation point of B, where B is some value where the first 25,000 ECH capacities didn't rule out an infinite staircase. And we found a bunch of A sub k's. So these are color coded. So for the orange stairs, these are the continued fractions. For the blue stairs, these are the continued fractions. And then for the yellow and brown stairs, you can see the continued fractions. And one final thing I'll point out is that for the yellow stairs, the continued fraction is 4 periodic. And for, I think, I'm fairly certain for all known infinite staircases, the continued fraction is 2 periodic at this point. So that is a new thing. And I, for one, am not sure exactly how that generalizes, but I think it maybe will lead us to some interesting stuff. Okay, so the proof is too long for now. Thank you so much.
Okay, thank you very much. If people want to clap, you can mute yourself. And if you have any questions for the speaker, you can post them in the chat or go right ahead and unmute yourself.
I have about this sequence of ECH capacities. So you had in your example 2, 5, and 20. So what was this for the blown up CP2? For which case was this 2, 5, 20?
This is for the Fibonacci stairs. This is the ball.
Fibonacci stairs inside of for the case of embedding to the ball.
Yeah.
Or I see. Okay.
Yeah,
so
but oh, sorry.
Okay, and each step is corresponds to some number in the ECH. Is this the statement?
Yes. Yeah.
Okay. Thank you.
Well, so it could correspond to many numbers. Actually, there could be several. Yeah.
Thanks.
Actually, I was going to ask, and it's good because maybe Grigory has something to say too. I mean, if you wanted to construct the embeddings for these infinite staircases explicitly, do you have any sense of how that might work? There's this recent preprint of Casals and Viana where they use almost toric vibrations to construct infinite staircases in these integral cases, but in these irrational cases.
I don't know. So also, I think it might be hard because I think in their case they consider full fillings, right? And so these are definitely not full fillings. There's some obstruction here from This one might, so the 8th ECH capacity often gives you this big obstruction after the accumulation point. So these are kind of poking out above the obstruction from the 8th ECH capacity. And I don't know, you would have to understand exactly where these obstructions intersected the obstruction from the 8th ECH capacity and then construct those full fillings. So I have no idea. Maybe it would be possible, but I think, I mean, the numerology in these things is really complicated. That would be even more complicated, probably.
Maybe just a remark that it I think to construct it from degeneration, the corresponding symplectic manifold has to be monotone, right? For example, 1/3 does it probably corresponds to the monotone case, right? If you cut it 1/3. So if it's not monotone, then probably this technique wouldn't work.
Okay, yeah, I don't know as much about embeddings, but yeah, thank you. Yeah.
Wait, why do they have to be monotone? To produce the embeddings? I mean, the ATF stuff, I don't think that requires monotone, does it?
No, I mean this particular construction from the toric degeneration. So if you want to use degenerations into this Markov triples, then okay. This particular one, yeah.
But just to remark that
the other thing that's weird is those almost toric vibrations. They definitely start at the sort of at the A = 1 side of the function, and they build up towards the accumulation point. So I'm a little mystified about the staircases that descend.
We have some that ascend, so maybe in these other cases, maybe we could do
it. And can I just make a remark about the most recent conversation? I mean, it's still in terms of well, yeah, maybe I don't have a remark, but I have a question. In the descending case, do you know what happens to the left of the accumulation point?
Yeah, so I think
maybe you were saying that even, but I didn't.
No, I didn't. I think I would really like to understand this. So I think what's happening is I mean, I haven't thought a ton about this. Well, I've thought very vaguely about it. I think in the descending case, what's happening is there's some obstruction, this thing down here, that has sort of was blocking the accumulation point and has now moved down, if that makes sense. So this horizontal line comes from some other obstruction that maybe was covering the accumulation point and has moved down. And then the ascending ones kind of occur when you vary B through an interval where, the ascending ones might occur where you vary B through an interval where there's an obstruction over the accumulation point that moves up and no longer blocks it. So
is the graph always flat to the left of the, if you look at the embedding function, I'm not sure I actually understand this picture, but the blue line there is flat. Do you know is that a general phenomenon that if I go to the accumulation point and then go to the left,
so far as I can tell, for the descending staircases, I'm pretty sure yes.
I see. That's pretty cool.
Yeah, so I think what's happening is you have these, so we talked about these obstructions ruling out a certain interval of B values. And so what it seems to be happening is that at either end of those values of B that are ruled out, you get an infinite staircase, and they're either going to sort of look like this with the flat graph on the left, or they're going to look like the traditional ones with the sloped graph on the right and the stairs coming from the left.